Okay, I'm going to work a few examples of the ratio test for convergence here. I think there's 4 of them. And these are all problems out of the Stewart Kokoska textbook, if you're wondering the source of these problems. And this is a just quick reminder of the ratio test to do the limit as n goes to infinity of the n plus first term over the nth term. And you see if you get less than 1 means converge, greater than 1 means diverge. And if it equals 1, that is inconclusive, and you have to go to a second test. And I do have the Auburn basketball game in the SEC tournament on over here, so I'm a little bit distracted. Hopefully I can get through this video without being too distracted by that. So number 17, I'll see the combination of an exponential along with a power function in the denominator. So that's one of the things I look for that kind of triggers my thought that this might need to be done with the ratio test. So I'll do the limit as n goes to infinity. And for the n plus first term, it's going to be negative 2 to the n plus 1 divided by n plus 1 squared. There's my n plus first term, and I'm supposed to divide by that term, but if you divide by the original series, that'll be the same as multiplying by its reciprocal, so I'll have n squared over negative 2 to the nth power. And now I'm looking at this, so I start to cancel what I can, and I have negative 2's on top and bottom, and it looks like I have n plus 1 on top and n on bottom. I can cancel this with all but one of those. And in my next step, as I clean this up, I'm also going to consider how the absolute values are impacting this ratio. And they will get rid of that negative, well, not get rid of, but the magnitude of negative 2 is positive 2. So that's going to be 2n squared over n plus 1 squared. And I now have a limit where top degree and bottom degrees are equal, and therefore I can divide their coefficients, and I get an answer of 2. 2 is greater than 1. Therefore, this series does indeed diverge. So we have a divergent series for number 17, and that was a pretty clean ratio test. Nothing too tricky there. Let's look at this is number 18. And number 18, we see, let's see, I see exponential pieces, 3 to the n and 2 to the n. I also see a power function of n cubed. And so that, again, is what triggers the thought that maybe the ratio test is the right approach. And so I'll set that up, the limit, as n goes to infinity of the absolute value. And I'm going to stick that negative 1 up on top of the fraction with that 3 to the n. So negative 1 to the n minus 1. Then, wait. Excuse me. I'm plugging in n plus 1 for n. So n plus 1 minus 1 will be n. 3 to the n plus 1. 2 to the n plus 1. And n plus 1 to the cubed. Then times the reciprocal of the original, which would be 2 to the n, 3 n cubed. All divided by negative 1 to the n minus 1. And 3 to the n. And so now I'll look at that and I see what can divide away. And let's see. So let's see. I have one more 3 on top than I have on bottom. So 3 to the n and 3 to the n plus 1. That will leave a single 3 in the numerator. Same thing's going to happen with the 2 to the n, and the 2 to the n plus 1 is going to leave a single 2 in the denominator. I can't do anything with the n plus 1 cubed and the n cubed. Let's see, negative 1 to the n minus 1, negative 1 to the n. I have one more negative 1 on top, so this is going to cancel with all of those. Now, technically, that's not really going to matter a whole lot because when I apply the absolute value of this one, n goes to infinity, the absolute value of negative 1 is positive 1, so that negative 1 is going to basically disappear as it becomes a positive 1. Then I have 3 times n cubed. And then in the denominator, I'm left with a 2 and an n plus 1 cubed, which leaves me with a limit of 3 over 2. Yeah, top degree and bottom degree are equal again, so that's 3 over 2. That, again, is greater than 1. Therefore, this one diverges as well. So there's the ratio test for number 30 here. And before I go on to the next one, I thought maybe it would be good just to give full credit to the author of these problems. So I'm looking at this book. Oh, wait. Green. Okay, so this is the Stewart Kokoska book. There we go, that I'm using. And it's actually on page 706 on this page right here. So if you go to page 706 of this book, if you happen to have this textbook, that is where I'm getting these problems. And let me shrink myself up here. There we go. And let's go on to the next problem. Let's see what we have here. 100 or n factorial over 100 to the n. Okay, so I see an exponential piece and a factorial. The combination of those, again, makes me think let's just go on with the ratio test. The limit as n goes to infinity of the n plus first term, so n plus 1 factorial over 100 to the n plus 1 times the reciprocal of the original, 100 to the n over n factorial. And I believe I have maybe chosen some bad examples here. Not necessarily bad examples, but what's going to happen on this one? Let's see. I have one more 100 in the denominator. N plus 1 is 1 more than n, so those will divide away, leaving just the 100 in the denominator. And n plus 1 factorial and n factorial, well, n plus 1 factorial is the same thing as n plus 1 times n factorial. And then I can cancel the n factorials. That leaves me with the limit as n goes to infinity of, and I can drop the absolute values because this is an always positive series anyway. And so I'll be left with n plus 1 in the numerator and 100 in the denominator. And as n goes to infinity, that is blowing up. That's approaching infinity, which again is greater than 1. And so what I was seeing a minute ago is that maybe these are not the best examples because I seem to have randomly chosen a bunch of divergent series. And so the first three all diverge. You're looking for a limit that is less than 1 for a convergent situation. And now 23, for the sake of practicing the ratio test, I decided to go ahead and apply the ratio test to this one. However, in the world of series and in limits here, certain functions are much powerful than other functions. And your general hierarchy of functions is that a natural log function is always going to be weaker than a power function. A power function will always be weaker than an exponential function, and an exponential function will always be weaker than a factorial. The one little caveat is that p must be greater than 1. P must be greater than 0, and your base of the exponential function must be greater than 1. So as long as p is greater than 0 and a is greater than 1, that's your hierarchy of functions. And so I'm looking at this guy, n factorial. While 100 to the n is a pretty powerful exponential function, that factorial is still greater than that. So if you wanted to apply the nth term test to this one, the limit as n goes to infinity of n factorial over 100 to the n power, that's going to blow up. That is a very top-heavy function. That is not equal to 0. Therefore, this is going to diverge by the nth term test. And that would have been a little bit more efficient than the ratio test, but I decided to jump into the ratio test anyway, just for the sake of practicing nth term, just for the sake of practicing the ratio test, nth term test. Okay, and then I think I have one more example. Let's see what this one does. Maybe this one will converge. I don't know. I kind of think it will, but at least I hope it will. This is really ugly. 2n factorial and then n factorial squared. How do you square a factorial? I think instead of calling that n factorial squared, it probably would be easier to think of it as 2n factorial over, let's just make that n factorial times n factorial. That's the same thing as factorial squared, is it not? And so I'm going to set that up with my ratio test. Limit as n goes to infinity. And this is an always positive function also. So the absolute values are not going to make a difference. However, if you're an AP Calculus student, get in the habit of writing those absolute values there as part of the setup, because it's very common on the AP exam to have to set up a ratio test and on the free response, and the absolute values are part of the setup. So you want to make sure you put those absolute values in there. So the n plus first term, that's going to be 2 times n plus 1 factorial. That's an interesting one. Over, and then I have n plus 1 factorial times n plus 1 factorial, and then times the reciprocal of the original, which would be n factorial over 2n factorial. And we need to see what's going to divide away on this one. And we again have a situation where I have n factorial and n plus 1 factorial, and that's going to divide away just like this. Where was it? It was this one, just like this example. So n factorial will cancel all but the n plus 1 out of the n plus 1 factorial. So I'm going to cancel this with everything except the factorial. So the n plus 1 is left. Same thing for this n factorial is going to leave just that n plus 1. Then I need to wrestle with this 2n plus 1 factorial. I'm going to move this down some to give me room to write above here. And so that would be 2n plus 2 factorial, which is the same thing as 2n plus 2 times 2n plus 1 times 2n factorial. And finally, I'm at a spot where I see how I can cancel things out. This 2n factorial is going to divide out that 2n factorial, and I will be left with the limit as n goes to infinity of, and now I can drop the absolute values. I'm going to consider that this is a positive series, and so the absolute values are not making a difference. I have on top 2n plus 2, 2n plus 1, all divided by n plus 1, n plus 1. And I'll be darned. I'll be daggummed. Once again, we have a case where top and bottom degrees are equal. If you expanded this numerator, that would be 4n squared plus a bunch of other stuff. The denominator is n squared plus a bunch of other stuff. That is 4 over 1. The answer to that limit is greater than 1. And so I kind of chose some bad examples because we didn't get a single case of a convergent series, but we did get some practice working with the ratio test. And really, the only thing I would need to do to make this a convergent series, if I wanted to tweak the problem, all I would have to do is change the series to its reciprocal. So if I did the series of n factorial squared over 2n factorial, that series would end up converging, because if you applied the ratio test to that, it's just going to flip what the answer was to the other, and we would get 1/4, which would be less than 1, which would show convergence. So that would converge. But the main thing I wanted to do is get some practice with the simplifying of the ratio test, and that's really where a lot of people have their difficulty with the ratio test. And there we go. So there are a few examples of how to use the ratio test to determine the convergence or divergence of a series. And if the ratio test does show convergence, which none of these did because I very poorly chose these problems, it would show absolute convergence. So just do keep that in mind. If something converges by the ratio test, it is absolutely convergent, not conditionally. And that's just something to remember as you're working these problems.